Hi, this is Jason, and welcome back to my astronomy channel. And so today we're going to be looking at how do we know about the distances to nearby stars. This is actually really interesting, and I really like to talk about the nature of what distances is and how we actually know things in astronomy, because frequently people don't know exactly how we know things. It's important to know that the most important fundamental things about astronomy are the fact that we gotta get distances to things to actually know anything. So let's look at some nearby stars. These are some of the nearest stars to us, and they're actually extraordinarily far away. They're on the order of light years or a few parsecs, and light years the distance light travels in a year. So these things are incredibly far away. They're trillions of miles away. Like the distance to the sun is 8 light minutes, but the distances to the stars inside of here are on the order of at least 4 to 10 to 15 to 20 light years, meaning light traveling 186,000 miles a second will take tens of years to get here from any of these stars that you see. Well, how do we actually know how far stars are? And the most important thing is to say, well, if we remember from a long time ago, people said the Earth goes around the sun. And wow, Earth does go around the sun does not go around the Earth, no matter what flat earthers will have you say. So since the Earth goes around the sun, we can use that fact to our effect. And if the Earth goes around the sun, we should see something a little like this, which is a thing called stellar parallax. Nearby stars should look like that they are moving back and forth in the sky, depending on where the Earth's position is around the sun. And so if you're lucky, meaning it's literally left and right around the sun, the Earth goes in an orbital plane, so if you're looking straight up out of the plane, you're not going to see much parallax. But if you're looking along the plane, you're going to see a lot of parallax. And so what we see is 4 stars in this picture going back and forth. We have approximately 4. There's one in the upper right that's not moving very much. The one in the lower left and the middle left is moving a little bit, but the 2 in the front are moving a lot. So the ones that are moving a lot, they're close. The ones that are moving a little are far. And in this picture, we see a lot of other stars that aren't moving. So that indicates that they are basically really far away and we can't detect the stellar parallax. So how does this actually work? So when a star is at some near distance, and the Earth represented by the blue dot and the sun represented by the yellow dot, let's say that's a nearby star and a little 5-pointed star there. And so we have a line going from the Earth to that nearby star, looking through to the background stars. So as the Earth goes around the sun, the apparent place in the sky that the star that is nearby apparently looks at is actually changing with respect to the background stars. Now let's take a look at a medium star, some star at some medium distance, meaning medium with respect to our ability to see it. And so now we see that the shift isn't as great with respect to the background stars. And if we go to a further star, we see that it's smaller still. And so let's look at the total angular shift of this nearby star, then look at the medium star, and then look at the very far star. Now I'm going to overlay all 3 of these things to show, wow, that's a confusing diagram, but let's get rid of the bits and just say, let's see what's the actual change. And I'll cut it in half to show that, because when we look at the stellar parallax, we define it to be half of this total shift. That's what we care about. We care about the half the total shift. That is what we define parallax to be. And now we have 3 parallax angles. Notice the long triangles, each of them are. Let's separate those out so it's a little easier to see. And now we have 3 long triangles with 3 stars at different points. And we can then say that the biggest parallax angle is for the one at the smallest length of the star distance, and the smallest parallax angle is for the farthest length star. So let's actually just look at one of them in particular, and we say, wait a second, that's a triangle. So from 10th grade geometry, we now know that the tangent of an angle, that angle is little p, is equal to the opposite divided by the adjacent angle in like 10th grade geometry from tangent. So that's the definition of tangent. And funny enough, the Earth's distance between the Earth and the sun is 1 astronomical unit. That's what we define it to be. We don't know what it is right now. We're going to pretend that we don't know. We know what it is, but let's pretend we don't. What we really don't know is the distance to that star. But if we can find the astronomical unit, and we can measure that angle P, then we know the distance to the star. So let's rearrange things because we're really trying to get the distance to that star. So we're going to find the astronomical unit, measure the stellar parallax, and then we'll keep going. All right, so our first step is let's measure that astronomical unit. So how do we do that? How do we actually measure the distance between the Earth and the Sun? Nobody's ever been there. We know it's 93 million miles or so, and people say that all the time. Everywhere you go, oh, the Earth's 93 million miles away from the Sun. It's like, how do we know that? Well, the basic way is we look at the sky and we check first looking at the phases of Venus. And this is a real trick. So the Earth goes around the Sun, Venus goes around the Sun, and Venus's orbit is inside the Earth's orbit around the Sun. Now, if you look really carefully what the arrow's pointing out, we have that the Venus is actually 50% illuminated. Wait a second. 50% illuminated means that it's half facing away towards the Sun, and we're seeing it directly in half. So we call it a last quarter moon, but if it's 50% illuminated, then it's in a particular position in its orbit around the Sun. And so let's just isolate it right there. And so now there's our isolated, so we have got better graphic things. So let's say if it's 50% illuminated, that means that it's at a 90-degree angle in the sky. So if you were on Venus, looking at the Sun and looking at the Earth, you would measure a 90-degree angle between the Earth and the Sun in the sky from Venus. That's if, from the Earth's perspective, Venus is 50% illuminated. Now this orange line we can measure, and we can measure that using radio telescopes and basically bouncing radar off of Venus. So when Venus is in this particular position, we bounce radar off of it, and it comes back. We measure that time distance to say how long does that radar signal get to. Standard radar distancing measurements called radar ranging. We can use big radio telescopes in order to help us do that. That gives us the geometric relationship between the Earth, Sun, Venus, so we get the radar distance. So that's one side of the triangle. Now we measure the angle between the Sun and Venus. So we have two measurement points. Now, when we back again to high school geometry, that's why we want to choose Venus at this particular location in the sky, because the astronomical unit is then the distance divided by the cosine of the angle, not the tangent of the side, the cosine. The cosine of that angle is the adjacent of that angle divided by the hypotenuse. And so we just rearrange the equation so that the hypotenuse is on the right-hand side, and we get that. Now, what's funny is those things are easy to measure. That angle is easy to measure. That radar distance is easy to measure. And so therefore, that's how we know that the astronomical unit is 150 million kilometers, or 93 million miles. And light takes about 8 minutes and 20 seconds to traverse the distance between the Sun and the Earth, from the Sun to the Earth. And this distance is the most fundamental distance we use in all of astronomy. We have to use this in order to get everything out to the universe, so making this initial measurement is critical. Well, first and foremost then, we use this distance to say, wow, we now know that the astronomical unit is this distance. Now what we need to do is we're still trying to find the distance of the star, so wait a second, what are typical parallax angles then for stars? Okay, that's a good question. We've said they move. We looked at that little graphic before, and we pretended that it's like as the Earth goes around the Sun, there should be some movement. But it's well known since antiquity that no one can see this with the naked eye. It's one of the most difficult measurements to actually make. And in fact, it took until 1838 for Sir William Bessel to measure the first parallax. It's about 1/3 of an arcsecond, or 11,000 times smaller than 1 degree. So what is 1 degree? 1 degree is approximately the angle that is subtended by your thumb when you hold it at arm's length and just close one eye and look at it. So if you take your thumb and hold it at arm's length and stick it up and take your thumb, that's 1 degree. Now make 60 little marks across your thumb, like from left to right, across the nail. And then in between each of those 60 marks, make 60 marks. So now there's 3,600 marks across your thumb, little tiny hair things. That is 1 arcsecond. So these things are really small. So 61 Cygni was the first measured parallax, and that parallax was approximately 1/3 of an arcsecond. So now take 1/3000th of the width of your thumb held at arm's length and take that and divide it into 3 parts. It's really a tiny, tiny thing. Now that means that the distance is about 3.5 parsecs. What's a parsec? Or 11 light years, 11.5 light years to that star. Now if we then say, what are some other typical parallaxes that are measured? The nearby stars, none of them, see I've bracketed them all of these are measured in milli-arcseconds. So we could have shown Bessel's measurement in milli-arcseconds, but you know, that would have been 300 or so. So now we have the largest possible parallax is about 768 milli-arcseconds, or 0.76 arcseconds. These are the nearest stars. So, wow, these are very tiny, tiny angles to measure, extraordinarily tiny angles to measure. And so, what is an arcsecond? Can we actually get an intuitive feel for that? Again, it's 360 degrees around the circle. Divide each degree into 60 parts, and divide each of those parts into 60 parts, and that's an arcsecond. Another way to think about it, you take a dime, put it 2.5 miles away, that's the angular size of 1 arcsecond, or a football 39 miles away would have that same size. So let's go back and say they're really small. So this triangle is really wrong. It should be more like this, because the angle between the Earth and the Sun is just under 90 degrees with respect to a distant star. The angle between the Sun, the Earth, and the star from the Sun is just about 90 degrees. So these things are so far away that looks like a box, not a triangle. So the P, while it looks big on this screen, is actually extraordinarily small, because both those other 2 angles on the right are almost right triangles. By definition, the one between the Sun and the Sun and Earth is. So the one between the Earth and the Sun is almost 90 degrees, but it's not quite. So let's go back up and see if we can do anything about this formula. See if we can use it to help us in any way. Can we make this thing easier? What happens when the angle is really, really, really small when we measure the tangent of it? Well, okay, now I'm going to throw something at you, because the tangent's pretty easy to understand geometrically. You say it's 1 AU over the distance of the star, opposite over adjacent. There's your geometric definition that you learned in high school. But if we then look at it as a trigonometric function, meaning we try to expand it out with a Taylor expansion and look at what it looks like as an infinite polynomial series, go look that up on Wikipedia or your favorite math book, so long as that angle x, now we use p because, you know, grab this thing and made this wonderful equation. But we have this particular infinite polynomial series on the right-hand side of the equation. We say it starts with x, with tangent of x now is the angle, and x cubed, x to the 5th, etc., etc. But if the x, or p in this case, is really small, then guess what? X is much bigger than x cubed, and it's really much bigger than x to the 5th. And every other term to the right is even more higher powers of x. So if the number x is really, 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 really small, then the tangent of the angle is essentially the angle. Well, in what numbers though? But wait, we've got to use the right units for this expression below. Arcseconds just doesn't work for this. Arcseconds is not how we would measure this in a trigonometric function. So what do we got to do? We now have to measure it the right way. A radian is a far more natural way of defining angles. Okay, what's a radian? Okay, take the radius of a circle and put it on the circle itself, and the distance around the circle that's equal to 1 radius is called 1 radian. It's approximately 57 degrees. And why do we care? Because look at this, we got a triangle here, and we're going to try to make something out of it. But why do we care about that arc? So we're measuring the angles in radians. So the green arc is 1 radian. So is the white arc. That is 1 radian. And radians are what you measure, the measurements that you need, because they're a distance, they're a length, and that's how we have to use that trigonometric function, which is a length. So let's go all the way over here and say, hey, we got a radian, which is the green thick arc, and the white thin arc in the middle. They're the same angular measurement. But let's now pull that blue line away from being a chord, a chord cutting across from the angle, but to going straight down. Now we've got a right triangle again. And if we then make the angle smaller, less than a radian, and keep going, we get a smaller and smaller angle. And if you notice, the thing is that that green arc is almost getting closer and closer and closer to being identical to the blue vertical line. So that's interesting. We want to make, and the angle is getting smaller and smaller and smaller. That's what we mean by the tangent of an x is almost equal to x, because it's the distance, it's the length difference. The trigonometric function, that big ugly function that we saw, is actually the length of that green outer thick arc. But we're approximating it by the vertical line. And the vertical line gets to become a really, really, really good approximation as that angle gets smaller and smaller and smaller. So now let's actually see how big these tick marks are. What we'll call radians is we'll call them some sort of tick mark going around a circle. We normally think of the tick marks going around a circle as being like 360 degrees, and in each degree there's 60 arc minutes, and each arc minute there's 60 arc seconds. But if we equate 360 degrees with 2 pi radians, we can then say how many arc seconds are there per radian. And that's a very small, tiny little bit. So we're making a conversion factor between arc seconds and radians. Remember, radians are actually the distance, are a measurement of the distance from the center of the circle to the edge of the circle. So a radian is a radius. So we're kind of relating an angular measurement to the radius. What is that size? Wait a second. If 1 radian is equal to a distance of 200, is actually equal to a distance of 206,265 astronomical units, if the angle, the little tiny white angle in the center, is exactly 1 arcsecond. That's fantastic. That's exactly what we're looking for. So we define the distance of a star to be a distance as the we make our definition of our unit. Our new unit is called a parsec, and we will look at that in just a second. But let's pretend that if you let that white little angle in the center get down to 1 arcsecond, then 1 radian is equal to 206,000, approximately equal to 206,265 arc seconds. So therefore, because 1 radian is the radius of a circle, we can now then define the parallax. A star with a parallax of 1 arcsecond has this distance that we call a parsec. A parsec is equal to 206,265 astronomical units, which is the same number of arcseconds around a circle. And remember, the circle length is almost the same as the distance, that vertical line in the triangle, the right triangle. So that's where we get that from. That's where we get that 206,265 AU from. It's because we're converting radians into arcseconds and defining 1 astronomical unit to be that tiny, tiny, tiny sliver across a circle. Well, that's equivalent to roughly 3.3¼ light years, or 30 trillion kilometers, which is a long ways away. All right, so now let's take this thing and flip it around, and we can clean up our little formula and say the distance to the star, then we'll call it d, is equal to 1 astronomical unit divided by the tangent of p. Well, we know p, for very, very, very tiny angles, can make the tangent of p equal just to p. So if we measure the parallax angle in arcseconds, and we use as our baseline 1 astronomical unit, because parallax is defined by observing things at Earth, because it's all Earth-centered. It's all Earth-Sun-centered stuff. Then the distance to the star is the distance in parsecs. So we now know that the parsec distance, which is this parallax of 1 arcsecond, that's where the word comes from, parsec. So we use this distance as our baseline. It is a geometric distance between the Earth and the Sun, and that's how we relate that to the distance to far stars. So now we go back to our original thing. We say all these stars are extraordinarily far away. That's where the 1, 2, 3 parsecs are. These stars are less. Everything within 1 parsec is one arcsecond. So 3 parsecs away, like 61 Cygni, is actually approximate, just under 3 parsecs, is a third of a arcsecond. So Proxima Centauri, the nearest one, is 1.3 parsecs away. That is the nearest star system to ourselves, which is roughly 4.2 light years. And the parallax is 768 milliarcseconds. That's the largest parallax of any star, and it's not even an arcsecond. So let's pretend if the distance between the Earth and the Sun was 1 centimeter, if 1 AU equaled 1 centimeter, then Proxima Centauri, the nearest star, would be 1.66 miles away, almost 2 miles away. And if we go to the next one, the fastest moving star across the sky, which is Barnard's star, it has a parallax of about half an arcsecond, and that's about 6 light years away, or 1.8 parsecs. So it's really far. And we go look at the brightest star in the sky, Sirius. Sirius would be about 2.5 miles away if our distance between the Earth and the Sun was 1 centimeter. Okay, why don't we use light years instead of parsecs? Because everybody likes light years. Light years are really cool. Everybody thinks cool light years, like, wow, how far light travels in a year. Well, light years don't work, principally because light doesn't carry a clock. So there's no clock on it to say, hey, light, how far did you travel? How long were you in the sky? And it goes, hey, well, let me check my clock. It's like, well, I've been gone for, I left that place 20 years ago, and now I'm here talking to you. It's like, no, light doesn't do that. Light can't tell you how long it's been traveling. We only know about the geometric distance to places. We can only get geometric distances through parallaxes. Light years are just an arbitrary thing that are used by science fiction writers. And remember, Kessel Run is a distance, not a time. So when somebody says they're doing something in so parsecs in time, they're saying something wrong. Anyway, so that is because parallax is a distance calculated from actual measurable quantities. Light years are not measurable quantities. It's a label we have that has a distance, sure. Light did take that long to get here from there. That is how long ago we are seeing something, so it is a look-back time. But because we know how far light travels in a second, but that's not what we measure. We measure geometrical distances, not watching the clock on a photon. Photons don't carry clocks. All right, so how have we done in sort of those kind of measurements? If we look closely, we've got these amazing measurements have been going on for centuries, and hundreds and thousands and millions of measurements have been made by astronomers. And finally, people said, let's make a big catalog. And so in the 90s, in the 80s and early 90s, the HIPPARCOS satellite, which is named after, it's named after the Greek astronomer Hipparchus, who did some of these early measurements, tried to measure the parallaxes, tried to get distances. So the HIPPARCOS satellite was in space for about 4 years, or at least it's still up there, it's not coming down. It operated for about 4 years. It measured approximately 100,000 stars within 1 milliarcsecond, and over 2.5 million with a lot less precision than that. So that was an amazing step forward. But the Gaia project, which was launched in 2014, and it collected over 1 billion stars as of 2016. In fact, it has done even more than that. Its final data catalog came out in 2022. Well, not its final, the most recent one, Data Release 3. And it'll probably have a final release roughly around 2027. But all of these things, this amazing satellite that can measure incredibly close parallax distances, can get them down to 1. So now Gaia has already released positions and motions for 1.4 billion stars, as well as parallaxes for 1.3 billion stars, down to microarcseconds. Remember, the nearest stars are measured in hundreds of milliarcseconds. These would be thousandths of milliarcseconds, or microarcseconds. This means we can, with the Gaia satellite, we're measuring distances directly out to 10,000 parsecs, which is an enormous distance. And that is incredibly important for physics, because once you know the distance to something, you can know, and you have a good idea about how bright something is, because when something's bright and it's far away, it looks dim. So if you know how bright it actually is, and you see how dim it appears to be, and you know how far it is, you can say, wow, I think that thing is so far, and now, because I know this kind of thing appears this bright, because we don't see how things bright actually are. We only see how bright they appear to be. But if we get the distance to something, we say, well, it appears to be this bright, but it's that far. So if we then trace it back, how bright would it be if it were closer, or everything was at the same distance? That's why it's important to get distances, because now we can get absolute brightnesses. So let's take a look at a map of nearby stars. This is a Gaia catalog of nearby stars out to about 100 parsecs, and this shows roughly the density of things. And the most dense region is off to the left there, the Hyades cluster. That is a cluster of stars that is nearby, and that cluster of stars kind of looks like this in the sky, and it's about 47 parsecs away. That's 153 light years for those of you who still must have light years. And you'll say, how long did light take to get here from there? 153 years. So the Hyades, when we look at it in the sky, we're seeing light that took 153 years to get here from there. Okay, why do we care about star clusters? Now, not all the stars in this image, just the group that's kind of in the center. See how it's kind of lightly over dense in the center of this image, and it kind of is more sparse on the sides? That's the cluster. And it's so close that it looks spread out. Well, why do we care? Well, notice that some of these stars look a little bit blue, some of them look a little bit yellow, and it's that color that matters. Because if we plot the color on the bottom and the brightness going on the y-axis up and down, we get a very funny thing. And that color says the redder it is, it goes to the right, and the bluer it is to the left. Wait a second, I used the words hotter there, and I got brighter on the left going up and down, but I have hotter? Stars are funny. Stars are really funny. The redder they are, the cooler they are. The bluer they are, the hotter they are. And you get this really interesting diagram called an HR diagram. And the HR diagram is the main tool for all of physics and astrophysics. It is the most important thing in all of astrophysics. And if you want to learn more about why it's the most important tool in all of astrophysics, come on, subscribe to my YouTube channel and go hunt around on my videos page to find stuff about the HR diagram. In the meantime, you can learn all sorts of interesting stuff about that. In fact, my entire YouTube channel is an entire undergraduate course in astronomy. So if you actually watch all my main videos, you will get the same exact education as if you went to a university and took a full semester class. In some places, it's actually more intensely in depth than your standard intro class, and it feels more like an introductory astrophysics class for astronomy majors. So swing on over to my channel, subscribe, and explore around and learn more about HR diagrams. See you later.